Welcome to this presentation of our PC-based balancing system as part of the Vibrometra software. Unbalance is a common machine fault. Unbalance occurs when the center of mass of a rotating part is outside its axis of rotation. An unbalance can be recognized by the excessive vibration at the rotational frequency. In time domain, there is a visible sine wave oscillation. In the frequency analysis, we see a high amplitude at the rotational frequency. Balancing takes place in certain steps, also called runs. The initial unbalance run measures the existing vibration. After this, a known temporary test mass is attached to a known position of the rotor. The next step is called test run. After this step, the amount and angle of the original unbalance are calculated based on the previous change in mass. Now a correction mass can be determined. The verification run checks whether the correction measure was successful. Piezoelectric accelerometers measure the amount of unbalance. A photoelectric reflex switch detects the angle position. One M312B interface box converts the sensor data into USB. In most cases, balancing should be carried out in two planes, which means at two positions along the rotor axis. However, if there is only one bearing or if the rotor is short in relation to its diameter, balancing in one plane can be sufficient, as shown in the following example. A note in advance: the help function, which you can access with the F1 key, provides you with support in all parts of the software. We enter the rotor data of the machine. The mass changes will take place at a radius of 50 mm. There are 16 fixed angle positions available for attaching masses. If required, a predefined balancing quality can be specified. Rotors to be balanced repeatedly can be saved. We want to achieve a balancing target of 0.3 mm per second vibration velocity. A specific balancing quality, or unbalanced mass, could also serve as a target. The settings for the vibration measurement remain unchanged in this example. You can enter the tolerance at which the rotation speed is valid and how many revolutions are to be measured. The feature test mass proposal will be explained later. The settings in measurement procedure also remain unchanged. The definition of the zero angle and the angle counting direction often raise questions. Therefore, the following advice: the balancing system cannot detect the direction of rotation itself. It is therefore specified that positive angles are counted against the direction of rotation. The zero angle can be specified in three different ways. 1. Speed mark and test mass at the same position, the zero angle. 2. Specification of an angle between the test mass and the speed mark. The zero angle is at the speed mark. The test mass angle is taken into account in the program. 3. Test mass at any position, an input of an angle of 0 degrees. Let's move on to practical balancing. At what speed should balancing take place? Balancing always involves mass changes. This can shift the resonance, which also causes a change in the phase angle. It may not be possible to reliably identify the influence of the test mass. The phase angle should therefore be as constant as possible at the used rotation speed. Resonances must be avoided. In this example, we are balancing at 2000 revolutions per minute. The unbalance measurement only begins when a constant rotation speed is reached. After 300 revolutions, we see that about 1.2 mm per second were measured at 62.5 degrees. This was the initial run. We will measure the resulting unbalance in the following test run. To do this, we attach a test mass of 1 gram to the rotor at fixed position number 9, which corresponds to an angle of 202 degrees. After confirming the details, we switch to the test run. The unbalance can now be determined. Here it is 147 gram-millimeters, or a vibration velocity of 0.95 millimeters per second at 337.5 degrees. Now the test mass can be removed. The software suggests corrections to eliminate the unbalance. As we work with fixed positions, two masses are always calculated, because the correction mass actually needed will be in most cases between the fixed angular positions. The following verification run measures the residual unbalance. The measured vibration velocity is smaller than our target value of 0.3 millimeters per second. The balancing process has been completed successfully. In many cases, however, it will be necessary to run through several mass changes and control runs before the desired result is achieved. The balancing process can be tracked in the Tools tab. We see that the test mass has already reduced the unbalance before we applied the calculated corrections. The polar diagram can be switched between vibration and unbalance. The balancing process can be easily documented using the report function. The included templates can be customized with text modules. We have shown the balancing in one plane. Balancing in two planes is very similar. In addition, there is only a second test run, with the attachment of a test mass to the second plane and the mass corrections for the second plane. Beginners often find it difficult to choose a suitable test mass. This can take a lot of time, especially for machines with long run-up and coast-down times. The balancing system provides support here. To use this feature, it is necessary to specify the approximate vibrating mass and the type of machine foundation. Furthermore, the accelerometer and rotation speed sensor should be in line. We have seen that mass can be attached to compensate an unbalance. Alternatively, it is also possible to remove mass. This can be done by drilling or milling, for example. Fixed masses can also be shifted concentrically or radially towards the center or the surface. In addition, an individual list of mass pieces can be created, from which the software suggests suitable combinations. The balancing software is available in 3 versions. You can find the differences in detail in the datasheet. We also offer kits for 1 or 2 plane balancing that contain all the necessary hardware and software components.